Okay, so like I've mentioned, we are preparing for the coming Saturdays after a very long break.
Hold on, sir. Must we join on video?
What's the problem? Is it your bundles that is running?
No, I don't have issues with bundles, but what I have seen, my experience with this thing is that when you okay, fine, join with video, but experience is that when you meet all of you on video, bandwidth gets very affected.
I think it's open. I think it's open. It's not a must for you to be on video. Maybe when you're talking, that's when you can engage video. But it's
that's what I thought.
Yeah. So it's open.
All right.
Okay. So I was saying, in preparation for subsequent Saturdays, we'll be driving our Saturday sessions through the projects that we are doing, especially the first intermediate group. So the theoretical parts is on a Q&A, and I was proposing between today and Friday, we spend time just brainstorming and discussing the concepts that I'm going to project. You guys are able to see. So for me, I'm just more like a coordinator and like the driver. But if someone feels that there's a concept that is missing, or they feel that they really want to explain a concept, they can actually chip in. And the chat session is also open. You could ask questions there. I'll be able to answer. And yeah, so today's session, actually, I was hoping to have a single session for this recap. But the way I prepare this content, it's quite huge, especially we are sitting all together. The guys who just finished the beginner, and the guys who are a bit in the intermediate. So for the intermediate guys, I'll ask you to bear with me, but this is a good opportunity for you guys to participate actively as well. So I'll just go through high level. If we're not able to cover everything today, then with your permission, we could agree on whether we continue tomorrow or Friday, but it needs to be before Saturday. So Saturday we'll have specific content for the specific groups. So I'm hoping to achieve, to go through the types of machine learning. We just go through them, open forum. If you don't speak, I'll ask questions and I'll pick people. So kama utaki kujibu, you log off. I'll pick you. And then we will review on the important aspects of machine learning, and we'll look at, hopefully, for each of the algorithms, we'll look at the important aspects, high level, through the slides. Anyone with a different approach or a question ahead of, before I just go to the next slide? Vincent, it's been a while.
Yeah, habari yako?
Salama sana, uko aje?
Niko poa, sijui kwanza leo unaweza nisikia hata.
Nakusikia kabisa. Carol.
Okay.
Okay. So hi Carol.
Hi.
Hi. Okay, so for the sake of time, I think we are already 13 minutes into. The first slide is just taking us through the types of machine learning. We've gone through this before, and what we covered so far in our previous classes: supervised learning, unsupervised learning, and reinforcement learning. Who can explain supervised quickly? Let's just engage. I know most of you guys have covered this. Dauliza mtu asipojibu in 2 minutes, I'll pick someone. Supervised learning. Carol, I'll pick on you now.
I think wako off.
Carol ameongea.
There's somebody on the chat anauliza if you can hear them.
Oh, Sling, they know.
Like 2 people.
Even Gideon.
Is this session recorded, Ayub?
Yeah, I'm going to record it. I've engaged the recording.
Like every session from now, it will be recorded, or?
Yeah, that's the plan. So I'll be recording and sharing.
Okay, that's good.
So Grace, but that doesn't mean you don't attend. It would be more lively if you attend. Let me tell you.
Yeah. It's the time. Even ukiniangalia sahi, like ndo nimeamka.
Ndio umeamka? All right.
Yeah,
Okay.
nimeamka.
Okay.
Like,
Just a note on that, before you go to the other person. I'm still, yes, I attended and I left for the other class, but I'm still not able to access that link. I had mentioned to you earlier.
Oh, yes. I figured there is also someone else who's not able to. I think immediately after this, when I'll be uploading this slide, this recording, I'll try and sort that out.
You should get a YouTube account and give us the link.
Will do, and I upload it over there. Hi, Silas. Good to see you. I think, Silas, you're on mute.
Hi, everyone.
Yeah. Now that's better. I can hear you. Okay. Tuendelee. Okay. So I'll go through the first slide. It's a recap, as I mentioned. Supervised learning and reinforcement learning. Things to note on supervised learning. It's for a supervised learning problem, machine learning problem, you know what to expect. So you're just organizing your data with an expectation. You know what to expect. Unsupervised learning, you really don't know how to expect. In supervised learning, there is something called labeling, and there is a target variable, which we call the dependent variable, because the determination of the output of that variable is dependent on other variables, which we call independent variables. So those are some of the highlights on supervised learning. On supervised learning, there is no target variable, and you don't know what to expect, but you're using algorithms to show you or to reveal to you a certain pattern depending on the features that you have. Highly used in, say, customer segmentation.
Can you hear me?
Yes, I can. That's Gideon?
This Gideon, yes. Okay.
Yes, I can hear you.
Thanks.
Karibu sana, Gideon.
Asante.
The session has started now. So unsupervised learning, and then there's reinforcement learning. There is a reward and punishment, mainly used in training sort of like machines, but also we have use cases for building chatbots using reinforcement learning. It's a bit deep, so for beginner and intermediate, those are some of the things that we've gone through. Yeah. And there is always a process flow. It differs between, there is no standard process for machine learning. It differs as you, depending on the algorithm that you use. But by and large, the fundamentals are the same. So the diagram you're actually looking at right now are the fundamentals of any machine learning process. So with machine learning, you have to get, what is it called? Data, because we are working with data. Okay, there is someone who has not muted. Is it Josephine? Josephine, could you kindly mute? I think her connection is a bit slow. All right, so with machine learning, we must get data, and there are some fundamental processes that needs to be followed. Once you get that data, you need to pre-process it. When you're processing it into either structured in a format that you can actually expose a learning algorithm into it. Once you do data preparation, you actually generate a model. In our previous classes, I mentioned that a model is equivalent to an algorithm plus data. So in the simple mathematical formula, a model equals to algorithm plus data. Once you get your model, depending on your satisfaction or the satisfaction of your customer, you can now either iterate to achieve your desired results, and there are several ways of tracking the metrics or performance of a model. Once you've achieved a certain metric, you can deploy it to a production for it to be used through either applications or I think most models are actually used through applications. Rarely will you find models being used through Jupyter Notebook or even Anaconda. So you need to deploy this production for it to be used. So what I'm going to go through are the different sections. Before I go through the different sections of importing, is there anyone with a question, anything to add? Okay, so if there isn't, I'll ask questions now. Masi, karibu sana. Carol, I'll ask you. Carol, are you online? Okay, Masi Mwangi.
Yes.
Karibu, I want to throw a question to you.
Okay.
Give me one supervised algorithm.
Regression algorithm. Is a regression an algorithm?
Linear regression, yeah, that's correct.
Yeah.
All right. Daudi, karibu sana. Unsupervised. Niambie one of the unsupervised. Nakusikia. Nakusikia.
Sorry. Unsupervised.
Yeah.
At the moment, hakuna jina kumbuka.
Danson.
I'm just blank. I have landed right now.
I got you off guard. Okay, you settle in. No worries. You settle in. So Danson is just logged in. Okay, what's it, Pachi Danson? I think guys are logging in. Huh?
Can I take that one?
Yes, please.
Try it.
Clustering.
Yes. That's Grace, yes?
Yeah.
Yeah, clustering is one of them. Yeah. So Masi, you had mentioned linear regression. What are some of the guides on linear regression? How does it work? What are some of the guiding principles?
Can someone answer that when I'm thinking?
Okay. As you think, Grace, please just tell us more about the clustering you've mentioned.
Hello, can you guys hear me?
Yes, now we can.
Okay, so from what I remember, I think we were dividing the data points, and then we group the ones with similar traits together, or the ones that appear to be similar together.
For clustering, yeah?
Yeah.
Yes. Any other contributor? There's someone playing with my screen. Is it my screen or you guys can see this? Ama we've been hacked. Ama we've been hacked. Kuna jamaa anatuchokoza.
Tuendelee tu.
Oh, okay.
I'm sorry about that.
That was you.
That was my screen. I thought my screen was having some problem because I can't see it on my screen.
Oh, okay. I hope hata tuwekea hapa vitu zingine zinatushtua. I took several precautions, but clearly. Anyway, wacha afanye ile anataka. Anyway, we were on clustering, yes? So, Grace, any other thing on clustering? An algorithm for clustering?
I can help.
Yes, please go ahead.
Okay, we have the k-means.
Okay.
Yeah, I can only remember the k-means.
Okay.
Yeah.
So how does k-means work?
It was about the distance. Trying to group the points that they are similar.
Yes.
Yeah.
Okay. So for the sake of
I have a question.
Yes, go ahead. Yes, go ahead.
Oh yeah. So if I remember well, the SVM also like works on clustering and then splitting them on a hyperplane. Can we say still unsupervised or?
For SVM, you can use it both. It is actually supervised. SVM is supervised. You can use it for regression and classification.
Support vector machines.
But that one is classification, not clustering. Clustering is on unsupervised.
Oh, okay. Yeah.
Okay, so there is something else on clustering where we have centroids, like you define your K, where, for instance, you have a huge data set and you want to just study what is unique about this data set. For example, the way we are in class right now, we could each fill in an Excel sheet. We enter our in a single row, I enter my name, my age, where I live, if I have corona or not. So those are 4 features. And then determine whether I'll go out or I won't go out tomorrow. So if we didn't have that target variable, whether or not I'll go out, so we have 4 features and we really cannot, okay. For us guys to make any sense out of all that data, we needed to look at all those people who filled in that Excel sheet. Or we can equally ask the machine to help us try and figure out how many groups, for instance, how many groups are in this Excel sheet. So the machine would now look at our age and probably where we live and any other feature that is available and strike a correlation and group us accordingly. So if we specify to the machine, or rather to the algorithm, this data of 100 people, split it into 3. I want to see what are the 3 unique groups that can come out. So the machine could use a combination of all the features, or it could use 1 or 2, some features. And the way we tell the machine or the algorithm to do that grouping is we specify a number which we call K. So that number, we could say K equals to 3. So what it does, it creates 3 centroids within which it will iterate, and the default centroids will, the default 3 centroids through an iteration will collectively bring together similar data points. And similar data points, ikiona myself and a few guys who are older. Maybe we are older and we live in the same estate, or we live in the same estate, or we have corona, living in different estates within the same bath. We will be pulled towards one centroid, and another group will be pulled towards another centroid. So basically, that is how clustering works. So it doesn't have labels. Once it finishes its iteration, that's the time now we open. Think of it like it puts the data points in a box. We open up, and then we find, okay, this is a group of people who are older. This is a group of people who are older with corona or older without corona. Whatever thing that the machine feels based on the features it was given. All right. Mercy.
Yes.
You are told us to give you time. You think about linear regression. Do you want to give it a shot?
There's someone talking.
Okay, I've just muted them. I think there's someone who's logged into both mobile and computer, so there is an echo.
Okay, so there are 2 types of linear regressions. There is a simple linear regression where you have one feature and one label. Then the second one, you have the multiple regression, you have many features and one label. So for simple linear, okay, both of them work with continuous data. Yeah, the data should be continuous.
Okay. All right.
Yeah.
That's accurate. That's very accurate. So the slide that we are all looking at, that was just a recap of the supervised and unsupervised. Where unsupervised, we've picked out clustering and gave out k-means as one of the algorithm used in clustering, and the linear regression as one of those that is used in supervised. Yes, someone is asking if we have polynomial regression. Yes, that is also there, polynomial regression. And also we have contributions in chat. Linear regression is establishing a relationship between independent variables and dependent variables by fitting the line of best fit. Yes, that is very, very accurate, Chris. Silas, do you want to give us more info on polynomial regression as well? Or I give it a...
Well, I think it's just the aspect that you have more features, and you're not able to entirely be able to get a straight line. So you use polynomial based on factors, whether it's a factor of 2, 3, all the way to, can't remember whether it's 8 or stuff. So it follows not a straight line kind of scenario.
Yeah, there is another thing about polynomial. You also need, if you find that you have a set of features that are not linearly related, polynomial is a good shot to do a certain prediction on that data set. And I think in class we were using, in our supermarket data set, we noticed that most of the features are not linearly related. So in our prediction, polynomial gave better results. Yeah, so Silas, yes, that is another one. There is also someone has mentioned picking, let me just maximize this, oops. Just a minute. Yeah, in linear regression, there is continuous data as the output. And another thing about regression, when your X or your independent variable is time, then you're actually making future predictions. But if it's any other independent variables is any other value, then you're just predicting unknown values, but not of the future, but now the current state. It could be, say, salary of an employee. Yeah, but when it's time, you could be predicting the stock performance of a certain company. That is still, and it's under the name of time series problem. Okay, so we've covered quite some stuff on linear regression, supervised and unsupervised. And anyone who can mention anything about reinforcement learning?
Yes. I think it's reinforcement. You can hear me?
Yes, go ahead.
It's about rewards and penalties. So the algorithm, if it performs well, it gets a reward. If it performs poorly, it's penalized.
Absolutely.
It's a feedback, kind of a feedback.
Yeah, that's absolutely correct. Give an example especially with people working with robotics. Yeah. So there is another question. There is another contribution from chat. Someone has mentioned, Felista has mentioned about assumptions. Yes, regression has several assumptions. Felista, do you want to take that away? Just tell us a bit more about the assumptions and why they're important.
I think we have the 4 main assumptions.
Mm-hmm.
Yeah, I can't really recall all of them, but we have the
homoscedasticity, yes.
Yeah, and then you have this one that we usually consider the error term.
Mm-hmm.
Must be, not really. I can't really recall them. Let me just someone else to share.
Okay, anyone who wants to contribute, you can just say one of them or two. To start us off, the most common one is linearity. So we are looking at relationship of two or more variables, or in this case, independent variables being linearly related. Any other? The second one, homoscedasticity, the one that Felicity has mentioned.
I think if I remember well,
mm-hmm.
Heteroscedasticity and homoscedasticity were explaining the distribution of the standard error across the data, if I remember well.
That's correct.
So it has to be in a form of like either heteroscedasticity. Yeah, it was complicated. I don't remember which one was the correct one, but it was basically the distribution of standard error.
Yeah, absolutely. So an homoscedastic pattern it's an assumption that the standard error is normal. But if you plot, there is a plot called ggplot that helps you check that state if the standard error is normal or not. So Devi, you're right. The homoscedasticity and heteroscedasticity is based on the principle on the distribution of the standard error. So if it is straight, like now you plot your standard error residuals, you'll see a straight pattern, like more like a block. Then it means your data points or your standard errors are normal. Or you could put a ggplot, the probability plot, and if it fits within the line, then it's normal. That is the second way. But if you see, yes?
Yeah, 1 minute. Are you displaying what you are talking about on your screen, or?
No. This one is just a brainstorming session, but we have notebooks. We have notebooks for all this. It's just a recap of what we've done in class previously. But of course, this would trigger discussions. If there is anyone who needs the notebooks or even further explanation on any of these concepts, please share. I'll take notes and we can engage moving forward. So the slides for today are just high level. We are more like, we are just like having a general talk about what we've covered so far, trying to remind ourselves. Ama hiyo inakupoteza sana.
Zizi iko sawa, iko sawa. Ni venye saa lazima ni catch up sasa ndio.
Okay. I'll share the documentation. Isn't it zile classes to share attend most of what we are talking about. Okay. So when you see it is concept, it means it is heteroscedastic, and most probably you might want to try a different algorithm to solve your problem, because linear regression assumption is the standard error needs to be homoscedastic. There is quite a lot of input from you guys. Let me go through it. Linear regression assumption being considered. Yeah, we were on the assumptions. So we've mentioned two. The third one, anyone who wants to mention the third one? Erico? Erico, wewe upenda tu kuficha sura. So I can hardly see your eyes or your facial expression.
I'm just dark. Sikupenda kwangu.
Oh. Give us one of the assumptions for linear regression.
You already said that one. The assumption, there's also I think I've changing devices has mixed me a bit. Have you mentioned about the dependent and independent not having a relation or something?
The multicollinearity. Is that the independent features not relating to each other?
I think so, yes.
Yeah, that's multicollinearity. You're right. That is the third one. So multicollinearity just means that all your independent variables should be independent. You shouldn't have one variable most likely giving the same information as another. So in class, I gave an example of, should you have one column that has, is an output of a formula from subsequent columns, then there is multicollinearity. Yeah, so for
the assumption here,
yes,
Ayub, just to confirm, the assumption on the principle of multicollinearity is that the assumption is there is no or little multicollinearity that exists.
Yes.
Forgive my nearest stuff, but you get what I'm talking about.
Yes, yes.
That is the assumption I'm assuming, that it doesn't assume that they have one or more meaning correlations.
You're right, Chris. You're right. So if you have I could give an example of if one field was the parent's age. Yeah, just say parent's age. You don't say father, mother. So the first field is parent's age, and then, or say, for example, dad's age, and then mother's age is maybe 5 less father's age. And then child's age is 15 less mother's age. So you see, if you specify that in the formula, in an Excel sheet, those are 3 columns, and then you put them in as formula, it means the child's age is dependent on the mother's age, because you're deducting 15 from the mother's age for you to get the child's age. So if you look at it that way, then all those 3 fields are correlated. And the assumption of linear regression, multicollinearity shouldn't be there. The independent variables should be independent. So that's another assumption, multicollinearity. The fourth one, Vinny? Felista?
There is multivariate normality.
Okay. Explain to her. That is Sharon, yes?
Yeah, yeah.
Okay. Please give us more info.
The data should be normally distributed according to multivariate normality.
Okay. Okay. That is it. It's for okay. All right. So there is assumptions for regression. Let me just look at the chart. What else can you say about either a supervised and unsupervised? Someone is asking, I'll push this through to the floor. Someone is asking, curvilinear and polynomial regression. Is it the same, one and the same thing?
Okay. From what I read about polynomial regression is that it has a curvilinear relationship. Like when you plot the data has a curvilinear relationship, meaning that it gives a curve, not a straight line, like a very good curve. Yeah.
Okay.
Yeah, that is.
Okay. Now there is another one that has been mentioned, logistic regression. Is it a classification or is it a regressor? Is logistic regression a regressor or a classifier? Gidi, do you want to try that?
It's a classifier.
Okay. Give us more details, a bit more details about how it works.
How it works. I think based on your problem, which you're trying to classify. So if you have a problem which has three classes, then it's able to do what do you call this? It's able to come up with linear. It comes up with k classifiers of your data of what you're looking for. So if you have, let's say, 5 classes, it comes up with 5 k classifiers. Then the one which returns the highest is the class.
Okay. Okay. Let me just rephrase what Gidi has just explained. So logistic regression operates under something. The name is a bit technical, but it's something called a sigmoid function. So it tries and fits all your values, especially the target variable, between 0 and 1, and it sets a certain threshold. So as Gidi has explained, yes, it is a classifier, and once you're doing a certain prediction, your classes, the number of classes you can have as many as your data allows you to have, depending on the problem statement you're solving. But the most common and simple classes would be, for example, sentiment analysis. We have 3 classes. That is happy, sad, or neutral. Another class, another problem that we could pick the number of classes would be, this dude has corona, has no corona. You can think of as many as you can. So what logistic regression algorithm does, it exposes, it subjects this data into a sigmoid function and tries and fits in the target variable between 0 and 1. And based on a certain threshold, it can be one class or the other. So that is how it works for logistic regression. And it is a classifier. All right. Any question, anything that someone feels they can actually chip in, what we are leaving out, maybe a question they've not understood, because the more you talk about this term, the more it sticks and the more you get clarity. So I really, really want to encourage people to ask questions or even explain what they've learned or even explain what is not clear so that I can give them clarity. So far, we've just discussed about supervised and supervised reinforcement learning and the process flow that I've just projected.
Ayub, I have a
Yes?
question.
Shoot.
What is the difference between the categorical analysis and classification?
Okay, categorical analysis, I think you have to put it into context because categorical analysis is actually, it could mean you're looking at, you're analyzing categorical variables. But classification is you're looking at the entire data set with the intent of either classifying into one class or another. So you see when you're solving a classification problem, you might have both categorical and continuous data in your data set. So
okay.
Sorry?
Okay, continue.
Yeah. So I think if you're putting it into context, categorical analysis, it's the kind of analysis you give your categorical variables to try and understand more about either the impact those categorical variables might have in your model, or actually that you give a deeper analysis of your categorical variables to get an understanding of what would be the impact. And there are several techniques for that.
Okay. Thank you.
Oh, okay. All right. Anyone with a question? All right. So the slide that we're looking at right now, as I had mentioned earlier, is just a guide of the process flow when you're solving a machine learning problem. So any ML engineer must have data, and this data needs to be preprocessed into a structured format that an algorithm can work on. An algorithm is just a statistical and mathematical formulas that have been wrapped together. So within those formula, each algorithm has a set formula that it works with, and that formula needs to be fed data. When you feed that data, the formula is implemented through certain functions to generate a model. So a model is an algorithm subjected to data that understands certain patterns, yeah? And that model can be used to make predictions. So once you have a model that understands a certain pattern within the data, you can use that model to make predictions. And once you've done the model, you can actually deploy it. All right. So when you're doing a model, there are several tools that you can use. One of them is Jupyter Notebook, Spider. But now I'll walk through just high-level sections of your notebook where you do the importations. This is, I think, standard practice. You import the libraries that you use, because some of these libraries, some of these things, as I will explain as we go through the slides, the difficult part that we normally learn is for us guys to get to understand the workings of already set algorithms. But whenever we use them, some of these things we don't practically implement. The algorithm does it for us. I will explain that as we move forward. So those libraries, the one that you're using, including when you're using an algorithm that we have mentioned, whether it is a supervised algorithm, whether it is unsupervised algorithm, you need to import it into your Jupyter Notebook, before you start using it. Yeah. There's someone asking about, before I proceed, I've just seen a question. Is deployment same as automation? Okay. They are different actually. A deployment is an action within the automation process. So automation could be, automation could mean one of two things. Yeah. So you're enabling a program to execute a set of tasks. Yeah, so a simple automation would be, instead of you opening your email every single 8 a.m. in the morning when you wake up, you could automate it such that it only, okay, instead of you doing something like checking the state of your systems in the office. Now, let me think of something that is a bit general. If you look at your daily tasks, the ones that you do, you open an email, you find an email with an attachment, you open that attachment, it is an Excel sheet, you open that Excel sheet, and then you start filtering all alerts. In that Excel sheet, it's a list of alerts that you received at night. Instead of once you get it, maybe you get 4 emails, and then you open all those 4 Excel sheets, and then you sum them into one Excel sheet, and then you create a report. And the report tells you, we have 50 red alerts, 5 amber alerts, and 150 green alerts, as in basically the health is good. So instead of you doing that, you could write a script that actually automatically opens your email, automatically downloads those Excel sheets, opens them, combines them, and generates a summary. And that summary, instead of you opening it or it's being dumped somewhere, it sends you the summary via SMS. So you have nothing to do with opening emails anymore. Now that is automation on one angle. Another automation would be, that report is needed by another department. So it doesn't end there. You push this summary report to that department, and that department does whatever it is with that. Maybe they have a sequence of actions. So when you combine the actions that you've automated together with what the other department has done, that is an automated workflow. But now deployment is an action within the automation process. Maybe the model that actually helps you understand the categories of problems that you have, it is actually a model. So you write that model, you deploy it, and then your automation script get answers from that model. That is the answer I can give. I'm not so sure if it is clear. I think Chris, you're in the automation. If there is something you could add with that, the difference between deployment and automation.
I thought you explained it perfectly well, because automation is like there is a process, a manual process that you're automating. Like you give an example of writing a script to read your emails. And then when you write it, probably I have done it here. But for it to go to production, for it to work, I need to deploy. So it is like I created that system on my machine. But now I want to apply it to several departments so that it can now be used actually. Like you are saying, we write a model. We write the model in class, but only us have access to the model. If we put that model, I will expose that model to the web software interface other people can use. So this act of us exposing the model via web is the deployment part. That putting it into production is the deployment. The automation, of course, is the whole process since we identified the problem, created the script, and deployed. Now we have automated the process. That's what I can add.
Yeah, that makes sense. Okay, now once we've imported the library that we want to use, we can now go to Now there is importing of the libraries, and then if your data is stored in a CSV, if your data is stored in a database, wherever it is, it could be a data lake somewhere. So through the libraries that you've imported, one of them is pandas that we had imported. There are certain functions within this library that enables you to try and connect to all these data sources. So one of the data sources is Excel sheet. We've been using Excel sheet in our previous classes, but there are scenarios where you can connect directly to a database and read data directly from the database. So using pandas, you're able to import the data set, yeah? And that is a command for importing the data set. So the first one, import the libraries that you are going to use. The second one is, how do you connect to this data? Where is it stored? Because the previous slide, we've seen that an ML engineer works with data. Now, we have several functions. Once you have the data imported into your, once you have your data imported into your Jupyter notebook, I'm trying to find someone okay, I think Georges. Georges Karibu, we feel your presence, but I've muted you. Okay, so once we have the data set in our Jupyter notebook, now how do we handle this data? So there are several, again, we are going to manipulate this data using pandas, and there are certain functions that are really nifty to know. For example, selecting which values you want to work with. Who is not mute? I'm really trying to find. Is it only me or someone else can also hear that sound?
George unmuted.
We can hear.
Oh, it's coming from Georgia. Okay, all right, that's better. Yeah. Kwani George ameandika script ya ku-unmute?
Uko sure George sio hack?
I automate like deploy your script.
Automate like deploy. Okay, so I think now we've muted him. All right, now you have the data in your notebook. There are some key pandas functions that it's good you get to understand how they work. One that I wanted to highlight is iloc, the one that I've projected right now. So look at this, it is your data set. Now you want to select, in our classes, we've seen how we are separating independent variables from dependent variables. So based on what has been projected, the independent variables are X and the dependent variable is Y. So Y is what you're trying to predict. So in that data set that you've imported into your Jupyter notebook, it is important for you to separate this as well. Now, the way you're separating them, you can use other means, but this is the shortest. Using iloc, it's like a simpler way of separating the data set. So you look at this formula, there is these brackets, and there is a comma separating two values. So you can look at it like the comma is separating rows and columns. So it is this bracket, row, comma, column. Yeah. But now, if you want to find or to pick all the rows in that data set, you put this semicolon. Yeah. So this semicolon will tell you, will actually tell it will instruct pandas to only retrieve all the rows. But if you put something like say 0 semicolon 5, it will pick the first 5 rows. So this is something that you can play around with. But now when you go to the column, this would pick the last. It will pick every column apart from the last. So your X values, it will pick all the columns apart from the last, this -1. So the -1 is removing the last index. So this is a nifty way, shortcut that you need to understand how to use this iLock. It makes your life a bit easier. Okay, so we have our data. We want to now start handling data. One of the most important things to do is to handle missing data. So there are several things that you're doing when you're doing your EDA and data prep. But one of the most important thing is to handle missing data. You need to find a way of replacing either missing data or removing them, depending on your decision. So there are several reasons as to why you might want to remove missing data. There are several reasons why you might want to retain that missing data. So scikit-learn has a shortcut, especially if you want to replace it with a certain formula from your data set. It's called impute. So from the impute, you can use simple imputer. So basically what you're looking at is a function that would actually check out in your data set any missing value, calculate the mean for that column, and replace the missing value with the mean. Now, the fit function here, this one actually extracts the method's parameters. So if it is generating the mean, yeah, your for that specific column, so all the rows, you're passing all the rows, and you're considering columns from index 1 to index 3. Yes. So this one is to generate the mean. Once it has generated the mean, you transform. Transforming is actually now applying where you have the null values, you have to apply the mean. And then when you print the x, you'll see your new x independent variables with the calculated mean in place of the null. So I want to open it here for guys to just discuss. At what points do you think it would be necessary to just delete null values? Enrico? Eric?
Yeah. So to delete, the time to delete null values most of the time is mostly if you see that, let's say if it's a column, the column doesn't make really much impact, and mostly if you don't have like enough data to go by, like if it's a user and doesn't have the important features, majority of the important features, you can just remove that row. Some other times you might have to now work on the null values to replace, depending on the value you might see fit. If you decide the value is mean, that is all right, then use mean. Yeah.
Yeah. So we all need to know, we all need to be aware of when to retain the nulls, when to replace them, when to use mean to replace them, and basically how to handle null values. It is very, very important. Okay. So this goes to all right. Someone is asking what time the class is ending. It's ending, I think, 8 o'clock. So we have how many? We have an hour. So I'll keep time because I know this time it's precious. Okay. This is where I was explaining. You split. You separate your data. And then we also mentioned in our previous classes encoding techniques. So several of us had a lot of issues trying to implement one-hot encoding directly. So there is something that you needed to add on one-hot encoding, something called column transfer. You have two options: either do it manually by merging. You do one-hot encoding separate, or merge using column transfer. What you're looking in your screen is a combination of both, and it does exactly what you want to achieve when you one-hot encode. So if you look at this, the first three columns of this vector is 1, 2, 3. These were categorical values, and then the fourth column is a number. Yeah. So in that column transfer, it takes it is actually encoding that you're doing. You pick one-hot encoder, and then the 0 is the index you want to do one-hot encoding. So 0 is the first index, which initially was categorical. Now, when you do that, remainder pass-through is, this is what does the magic. Remainder, what this does is, it doesn't return only what you've one-hot encoded. It also returns the other columns that were in your data set. So at the end of it all, you have your X variables ready for to expose to an algorithm. There is one thing: once you fit transform and apply the encoding, you need to convert it to an array, because the algorithm only takes array. So this one is to make sure that this X variable is ready to be exposed to an array, to an algorithm. If you just transform it without passing it to an array, you'll get errors. So we have several encoding techniques. I just thought of bringing this as an important, it's important to know when to do encoding, whether or not it is necessary, how you need to do it, and also a reminder of other encoding techniques. There are quite a number. Label encoder. Who can mention another encoding? Sling. They know. But I don't think we've covered this we were just starting. Grace?
Binary encoding.
Yes, binary encoding. There are quite a number. I think we covered this in intermediate. So it's important to know when to use which one, why, what are their strengths, and at what point should you use them, or what is the impact of each of these in your modeling process. So this, what you're seeing here, is exactly what has been encoded. You look at the country, the age, the salary, and whether it was purchased or not. All right. Now, the most common method being used nowadays to separate data set is train, test, split. This is also important to understand what's going on. So train, test, split. You can't train your model, especially supervised, without using a train, test, split with model selection a class in sklearn library. So when you look at this, let me explain what this does. These are the outputs: xtrain, xtest, ytrain, ytest. These are the outputs. So this function, it's called the function is called train, test, split. And train, test, split, you pass into it certain parameters. And that parameter, the first one is x. Remember previously you separated your data into x, y. So x are your independent variables, y is your target variable. And then test size is basically, out of your data set, what percentage do you want it to be test? So in this case, it is 20%. So the 80% is to be used for training. So random state is an integer that actually freezes the state. It freezes the data set in a certain state without it changing, so that any subsequent functions you expose to that data make references to the same state. So when you'll be displaying.
Ayub, hold on. I want to clarify something on this.
Yes,
so what
yes.
we are doing, we reported, we have a data set. For example, we have a data set like it's 5,000,
yes.
5,000 columns of data,
yes.
and we want to use it to train our model.
Yes.
So we imported the whole of it. This
yes.
function here, we are splitting that data. For example, using this example where you are saying 20%, that should be 1,200. We freeze it. So when we are doing the analysis and the training of the model, we'll only use 80%. And then we come back and re-import the 20% to test the model. Is that what you're saying?
Absolutely. That's absolutely it. So you use the 20% to validate the model you've trained. So you need to separate it. So this is the function that actually separates it. And as it separates it, it gives you several lists. The first list is for the one that you will use for training, which is xtrain. The one that you'll use for testing, which is xtest, and the y variable that you'll use for training, and the y variable that you'll use for testing. So you've got it correct. Okay. There is something called feature scaling. So feature scaling is also an important thing that we all need to be aware of in our ML workflow. So what it does is, for instance, if you have variables or a column that has several values, and those values range in a significant way, you might find it important to fit all those values into a certain range so that the dominant one do not take precedence. So for example, if you're looking at salaries, someone earning 10,000, and within the same organization, we have someone earning 12 million. So if we have majority of guys earning between 10,000 and 500,000, the guy earning 12 million will be an outlier. But to neutralize the impact of the dominance of that guy earning 12 million, you could decide to fit all these salary values within a certain range. And for standardization, this normally fits all values between -3 and 3. And for normalization, -1 and 1. So depending on the method that you choose, and we also need to know when to use which method. Normalization is normally used in most cases when the data we're working with is in a normal, displays normal distribution. So we in class, we covered about distribution types. So when you see your data is normally distributed, you could choose normalization. And standardization, you can always use this all the time. This one is a perfect fit and the most preferred, because whether your data is normalized or not, you can always use standardization. And that one is a formula for standardizing. So you take the X value, deduct from the mean of that column, and divide by the standard deviation. So you get your standard representation of the same data point. Yes, George has also added in the group that you can also consider train test split to separate data into training data and validation data. George, that is absolutely right. Okay, so in feature scaling, when we are dealing with variables that we feel it's important to standardize, we can use one of these ways to feature scale. Any question?
Hello, sorry, my link keeps going off, yeah?
No problem. Pole about that.
When you're doing your, sorry, taking guys really back, Kabisa. This whole feature scaling, is it, or can you also use it to, were you saying that you're using it to fill in null values, or what were you doing with it?
No, feature scaling is for you to like standardize all the values in a certain column. It could be a column for salaries, for instance, that you want to fit in within a certain range, so that the dominance, you might have one person, you got the point, yeah? So we neutralize the dominance of one or two or two observations. That's the way to neutralize it. Okay. So any other question? I'm going to ask a question here. Oh
I
yeah.
have a question.
Yes, Carol.
Now there is this term feature engineering.
Mm-hmm.
Is it a term that like summarizes like feature scaling, dealing with the null values, encoding, all of them?
And not quite. Feature engineering encompasses. It's actually it's a way, a technique of achieving generalization of your data. For instance, you might have certain columns that are very, very specific, that you feel as the domain expertise, if you feel, if you work with your model the way the data is, it might lead to something called overfitting. So feature engineering is a way in which you can come up with your own representation of the same data that generalizes your data. I'll give an example. If we have, we all work, okay, we've been in an environment where when you call Kenya Power, they tell you your ticket number is this. When you call Safaricom, they might give you an information that this is your reference number. When you go to a bank, they give you, if you have an issue, yeah? So let's think the way the backend works. So the backend works, that ticket has several categories. It could be, if it's in the case of a bank, it could be a bank loan, or it could be a bank complaint, withdrawal complaint, or a deposit complaint. So underneath deposit complaint, we have ATM deposit complaint, we have teller deposit complaint. So if you have a model that has several columns, including teller deposit complaints, you have one column that says bank complaints, and then another column now specifies it was ATM deposit complaint, it was teller complaint, it was, when you work with the specific complaint to build a certain model, in your own judgment, you might find that, okay, I think if I do this, I might be leading my model to overfit. So overfitting is where the model cannot, it understands very, very well the data that it has been given. Should it be given new data, then it performs poorly. So you might want to redo the same model by creating a new column and call it bank complaints. And all this ATM, all this stuff, put them under this, such that your model will learn bank complaints and study the patterns and make a prediction. So that is playing around with those features, either to generalize, that is what is called feature engineering.
Okay.
Yeah.
Okay.
Any other question?
And when we do cross validation, is it like a replacement of the train, test, and split?
No, it's not. It's not a replacement.
Rather, when we do cross validation, we don't use train, test, and split.
Okay, it's just yeah, it's a preference depending on the problem you're solving.
Okay.
It's highly dependent on the problem you're solving.
Okay.
Just like for specific metrics, each algorithm has their own metrics. Any question? Okay, I had a question on this one. What do you guys think after understanding the impact of feature scaling? What do you guys think? Should this be an exercise being done before you split your data or after you split your data? Sharon?
I think before you split the data.
Okay.
Yeah.
You explain the reasoning behind that?
So, okay. Okay, ask someone else.
Okay. Who wants to give it a shot? Marcy? I'll just pick guys randomly. Who haven't I picked? Unajua mimi naweza kuwa mchokozi sana na kuna mtu tu anahepa. Vincent, what do you think? Just give the answer that comes to your mind. If you get it wrong, you'll never forget it once you get the answer. If you get it right, you'll be proud. Whichever way you'll be good.
I was thinking before you split your data.
I think it's before, eh?
Yeah, I think it's before.
Okay. Anyone who has a different thought? Josephine?
I'd say after.
After, okay. Your reasoning?
Pass.
Okay, all right. Two more guys before I give the answer. Gideon?
There's some people who are asking what is the question.
Oh, let me repeat. The question is, after understanding what feature scaling is, at what point do you think you need to do the feature scaling? Is it after splitting your data or before splitting your data?
I would still say as the rest before, because from the formula you could see aspects of mean and standard deviation.
Okay.
So you use the same mean and standard deviation to the whole population.
Okay. Yeah. All right.
I think you can do both.
You can do?
I think you can do you can do either before splitting or splitting. I think it's all the same.
Okay. All right. So, yes?
Yeah, I mentioned maybe it's before so that maybe you can like the data from that point onwards till you go and test will be like normalized, like everything you won't have like different because when you do afterwards, so like it will be like before your data and after the data could have different. But if you do it before, like from then on henceforth, the data itakuwa to normalize like everything there.
Okay. All right.
Ayub,
Yes.
also, if I try, I think if we do after, we will have to do both for training data and test that data. But if we do once, which is before splitting, just do once, and then when testing now using the test data, it will be sorted out.
Okay. All right. So those are varying answers, and I think I like it because all the explanations are justifiable to the answer, and I would want us to think of to remind ourselves why we do feature scaling in the first place and how it's done. If we look at the formula for feature scaling, let me just go back. For each data point, it takes and generates a certain standard value. Yeah. So if the mean of the entire population, okay, let's start with the proponents of doing it before the split. If we do it before the split, it means the entire population's mean will be considered, and when we are splitting it, the training will be working on a mean of the entire population, and the testing will be working on a mean of an entire population. Yeah. But the idea of training and splitting is for the model to be able to understand, based on the training data, can it do a certain prediction? So if the training data, model parameters extracted, like now what I've just projected, if we use the entire population, the results, especially the prediction results, might be skewed. So it is good practice to do it actually after. The standard scalar that you create is common to both. The standard scalar that you create is common to both. However, the feature scaling should be separated. So if I go to the next slide, yeah. So you see here we are creating an instance of a standard scalar which we will use on both. Now this fit transform actually does two things. The model parameters, like now the standard deviation, the mean, it extracts, the fit bit of it extracts those values. Now, once it extracts those values for the train, yeah, for the train data, which will be common on both, it transforms and implements, it applies now and generates the standard equivalent of the X value. So to answer the question, it is good practice to feature scale after you split. And when you're doing that, for the training data, you fit transform, but on the test data, you only transform.
Just repeat this last point, please.
For standard scalar, feature scaling, you do it after you've split your data. And then on the training data, you need to fit transform. Yeah. But on the test data, you only transform. Because you're using a common standard scalar for both X-train and X-tests. So if this is confusing, the take-home could be, for feature scaling, always just do it after you've split your data. And feature scaling does not apply in all datasets. There are some datasets or some problem statements that you don't have to do feature scaling. I read people saying very confusing. It's a good thing I brought it up. So it's inafaa tupambane kabisa mpaka tuelewe hii concept, because these are some of the tips that actually make have direct impact on the model results, especially with whether your model predictions are reliable or not. So if you must have feature scaling, always do it after you've split your data. Okay, we can have several subsequent classes on some of these issues that are not clear. I think for today was just a recap, and shikilia tu hapo hapo. We will have many of those. So I'll quickly go through some concepts for regression, and then maybe at the end, you guys will tell me if you find it appropriate, because I had prepared quite a lot of slides. I think they're around 50, because we've gone through, we were to go through data preparation, regression, classification, clustering, and a bit of NLP, an overview of what we have covered and what we will cover. So that on Saturdays, now we are working on notebooks as we handle the specific issues, like now further explanation on the feature scaling. So I was proposing, should today not be enough, we could have the same session tomorrow, same time, for 2 hours, cover some extent, and then Friday, we finish up, and then now subsequent, as we had planned previously, Saturdays become the days where we do the hands-on work, and then Wednesday becomes the days that we do NLP. So I'll quickly go through regression slides. Most of it we have covered in our previous discussions. And in class, we covered all these regression algorithms. There were 6 of them. So I'll just touch on, I'll touch on, I think maybe we have time for simple, multiple, and maybe polynomial. I don't know where the time will cut us short, but we don't want to rush. It's my wish that we understand. That's why I'm creating another time for tomorrow and Friday. So we go through the assumptions, which we have gone through previously in our brainstorming session earlier on. And then I'll also touch on simple linear regression, multiple linear regression, and then we could call it a day. And if, with your permission, we can either do it tomorrow and Friday, or we just catch up on Saturday. All right, so the assumptions, some of them we've mentioned. Linearity, we have normality, homoscedasticity, which is actually the opposite of heteroscedasticity, and then multicollinearity and autocorrelation. Yeah. So we had an understanding of linearity, normality. The residuals that results from the linear regression model should be normally distributed. Yeah, normal distribution of the residuals. Homoscedasticity. Yeah, dependent variable is equal across range of values of the predictors. Yeah, multicollinearity. If the independent variables are highly correlated. And then autocorrelation, the independence of the residuals. Autocorrelation is the residuals must be independent. There are several ways of measuring the assumptions of regression. Some are, one of them could be just plotting the homoscedasticity or heteroscedasticity scatter plot. And through the scatter plot, you'll be able to see visually, or using the probability plot, which is also called a GG plot. Yeah. All right, simple linear regression, y is equals to mx plus c. We went through this. The targets, the independent variable, the independent variable are the x's, and then we have coefficient and the constant. Okay, so for the constant would be like, for example, if you want to measure the relationship between the weight and height of an individual from the time they are born. So from the time you're born, you're not born at 0 kg. So you had maybe 3.5 kg, 3 kg. There's always a figure at the start. So if your target variable is weight, then if weight or height, the constant there becomes the 3 kg, the starting point. Assuming all the other values are 0, you are on day 0. You have a variable, you have a constant. So that is the relationship. Simple linear relationship looks at the relationship between two variables. In this case, it is x and y. Yeah. So yeah, this one is an example of salary. Right from graduate, you might start earning 30K, but as you gain experience, there is a rate of change in your salary. Maybe at the end of the year, you get increments or salary increment or bonuses. So those are problems that can be easily modeled through linear regression. The residuals, basically what you're trying to explain here is determining the line of best fit. In summation, the line of best fit is one that has the least number of summation of errors. Yeah, so that is the least number of summation of errors. So through a method called ordinary least squares method, several of these lines are drawn, and the one with the least sum of errors, least sum of residual errors, is the one that is picked as a line of best fit. Okay, that is the code for linear regression. You import the linear regression, create an object, and then fit it. So the function fit, what it does, it just picks, it executes the algorithm's formula and extracts what is required to generate the model. So it's blending the algorithm, the statistical techniques with the data to generate a model. Through that model, you can now run predictions. And predicting is as simple as doing a prediction to X test. So remember where we are splitting our data into X train, Y train, X test, Y test. Now you're predicting a set of X values. This is how you predict and store that data in a variable called YPred. You can visualize your results and see the line of best fit. Generally, it's not normally this easy or real life. You can also visualize the testing as compared to the training. Multiple linear regression is when you have multiple multiple independent variables, but it's more or less the same thing as linear. The only thing is you have multiple independent variables that contribute to your target variable. Now, this is a good case in point of explaining the multicollinearity. And the reason why I brought this here, it's because when you're doing encoding, especially one-hot encoding, this one came in class some time back. And someone asked, I think it was Sharon, someone asked why we needed to drop, or why is it recommended to drop one of the encoded values before you go to modeling. Yeah. So you'll notice that from what you're looking at in front of you, if we were to include the second variable, like for instance, the value for, in this case, once you have encoded the state column, you'll get the values dummy variables. So New York will be 1, 0, and the others 0, 1, 0, 1, 1, 0, 0, 1. So there are two, I think there are two cities. Now, if you include California and not drop it, what this would do, California will be a formula for New York. So if you want to get California, it is 1 minus. If you want to get California, it would be 1 minus New York. So 1 minus 1 is 0. So that is a formula. And remember what we spoke about multicollinearity, and whatever information one variable has should not be implied by another feature. Otherwise, you drop that feature. That is the main reason why when you do an autoencoding, you always keep 1 n minus 1. You only include those variables. I hope it's clear. Sharon, that was you who asked that question, yes? I don't know if you can remember.
Yeah, it was me.
Okay.
Yeah.
I thought it wise to bring it up because there are guys who might be asking the same question in this forum. I can see there are some questions. Let me just go through. Okay. There is network complaints. Okay.
Ayub.
Yes.
So suppose on that state variable, you didn't have two cities, you had, or rather 2 states, you had more.
Yes.
So let's say 4 or 5, and then you
Yes.
create them into dummy variables.
Yes.
So in that case, is it really possible to drop?
Yeah, it's still necessary to drop the last one. The last one will always be implied because it's normally implied. Because
so
if
you drop
you
drop the last one and keep the rest.
Yes. Okay. All right. I can see the guys complaining about network, and I think we have 15 minutes to time. So they'll be recording. I'll push this and make sure even the previous recording is also available for you guys to go through. So ahead, there is one concept of p-value. I think, Grace, you're a statistician. Hebu tuambie p-value ni nini? Kama nimekuseti.
No, sorry, I was on mute. Yes?
Okay. Just give us what you understand by p-value and how it plays around with multiple linear regression.
Okay. So p-value, I think the definition is just the probability of obtaining a result. So now when it comes to linear regression, once you calculate, you always get a p-value. Okay, so now can I so there's significant and insignificant. Eric, is this still a problem? Significant and insignificant.
No, at the moment.
Okay.
Well, I have to remember it, but it's okay. Go on.
Okay, so if it's significant, it's supposed to be less than 0.05. So a p-value which is greater than 0.05 is not significant. Any which is less than 0.05, that's significant.
Yeah, absolutely. So with a value less than, if you get a p-value less than 0.05, which is your significance level, you normally reject the hypothesis, the null hypothesis. You reject or you fail to reject? Which one is it? Grace?
Yes?
When
Sorry,
you have
my network has a bit of a problem.
No problem. When you have a p-value of less than your significance level, what do you do to the null hypothesis?
If it's, can you hear me?
Yes, I can hear you.
If it's less than 0.05, you reject the null hypothesis. Okay. But if it's greater, then you fail to reject the null hypothesis.
Absolutely. Okay. Felicity, I know you're also a statistician. What do you have to add?
On the p-value?
Yeah.
I think I have for 1 month I have not been doing statistics, so I think I'll go with that for.
Oh, okay.
Yeah.
All right. Okay. That's exactly what it is. Another way of looking at it is like what Grace had mentioned. It's the probability of observing, the probability of observing the results, given that the null hypothesis is true. So will you be able to see what you're seeing with the null hypothesis being true? If the probability is low, then you reject if it's low than the significant level, then you reject the null hypothesis. If it is higher, you fail to reject it. It means that it is not by chance. Okay?
I have a question.
Yes, shoot.
The null hypothesis must always be accompanied by an alternative hypothesis.
Absolutely.
So it means when you reject the null hypothesis, you are accepting the alternative hypothesis.
It's okay. In English, that is essentially it. But statistically, you don't always accept the alternative, because even the alternative can be subjected to a test. So it's always rejecting or failing to reject. So there's no, okay. I think statisticians would help here. I rarely come to a conclusion of accepting.
Okay, can I assist?
Yes, please go ahead.
When you fail to reject the null hypothesis, it doesn't necessarily means that the null hypothesis is true, but it only means that you don't have the sufficient evidence against the alternative.
Absolutely.
Yeah.
You have a real example, maybe to understand better.
Between the null hypothesis and alternative.
Yeah.
I think we should go back to the definition of what is null hypothesis and what is alternative hypothesis. Then from there, see, we usually say that the alternative, okay, like what is the basis of your research? Is it the null hypothesis or the alternative hypothesis?
It could be maybe going against, or it's always on null hypothesis.
Okay, let me assist with an example that you were given once. So suppose that someone says that a species has gone extinct. So when they say that, it's just an assumption. Since no one has seen the living species, now everyone is assuming that it has gone extinct. But later on, if the species shows up, for some reason someone finds evidence that they're still living, then this other assumption is thrown away. So as it has been mentioned, when you do not reject a null hypothesis, it doesn't mean that the alternative hypothesis is also correct. Someone can just come in and also dispute the alternative hypothesis.
Absolutely. Absolutely. I don't know, does it make sense?
Mimi najua tuko na gidi hapa tunashangaa. Sasa model yetu tukireject hii hypothesis, model inaishia hapo.
Unajua kuna statistics na kuna model. So when you're looking at statistics, what you're doing is you're doing a research, and you see one common thing about research can always be disputed with the exposure of new evidence. So what statistic does is, with the evidence, like what Felicity has said, there is no enough evidence to come to this conclusion. But let me say today I do a research and say a statistical research based on science. I've collected all the data, and I say that corona is highly infectious to male species in Nairobi. Yeah. So I study that, and that is my conclusion. Tomorrow, someone can dispute it by a completely new set of evidence. So if I accepted the alternative, or let me say in my research, I rejected my null hypothesis. That what I gave was my null hypothesis. If I rejected my null hypothesis, and in my conclusion as a research guy, I conclude that I accept the alternative hypothesis, which says that in Nairobi, male species, for example, are not affected. So tomorrow, with new evidence, if I had accepted, in tomorrow it will be difficult now. It won't be statistically correct. It's like it was concluded when the alternative was accepted. But because the alternative can also be disputed through a new set of research, then we never accept the alternative. We just fail to reject the null, because the null is the base. The null is like the base.
Okay, can I have some inputs?
Yes, please.
Yeah, when we reject the H naught, the null hypothesis, that's when we can say that we can accept the alternative hypothesis. But when we fail to reject, that's when we say that we don't have the enough evidence to even accept the alternative. Is it clear?
The conclusion.
Mm-hmm.
Can you statistically say that you accept the alternative hypothesis?
No, you can't say. If we usually okay, I think we usually have to use the null hypothesis. Either we reject her null or accept
you failed.
it.
Exactly.
Yep.
Yeah. Okay. Chris, you had asked a certain question. Ama umeelewa kabisa?
Oh, my question was, you see, now we went into statistics. You see statistics in a research, and I'm doing a research. I start with what is agreed from there, which I'll take as a null hypothesis.
Yes.
Then I do research. Either I accept that the norm is okay, or the norm is not okay, and this is my evidence. I think that is statistical, right?
Yes.
But I'm thinking in terms of this class, we are doing machine learning. We are looking forward to making models. So where does this sit in terms of the model?
Okay.
That is why I asked when you reject or don't reject, or where does it sit with the modeling?
Oh, okay.
What we are doing here.
Yeah, I understand. And I think that is going to be covered. We are going to cover that in our next class. You see, in the second intermediate class, we took a break when we had just started statistics. But in that class, you'll definitely see how the statistics play in role. As a matter of fact, statistics is a very, very big factor in machine learning. Very, very big. But utajua hiyo. I think we are 5 minutes, actually 4 minutes to time is up. I think I'll end in this slide. If there is no question, what we'll pick up? I think I'll set up another one tomorrow. I don't want to rush. We conclude, we continue recapping. And for any concept that is completely new, put it in your mind that subsequent classes, you're going to cover these items in much, much deeper. So it is for the interest for you to follow through tomorrow and Friday as well. So tomorrow we'll start from the technical lessons or methods of building models. How do we build models? We understand there are some features that we drop, there are some that we add. So how do we go about them? And what are some of the steps, especially with regards to regression? Iko swali? Is there anyone who has not spoken? Let me see. Danson alilogin akanyamaza tu. Daudi, Danson, uko na swali? Oops. Danson. Haya. Labda alilog out. Okay, George, Gidi, Grace, Josephine, Felista, Sharon, Silas, Deno, Vincent. Okay, I think we wrap it today. We continue tomorrow and Friday. So by Friday, we'll have finished all the recap. And then we will initiate our classes as usual. So there'll be beginner and intermediate. And we'll have all these sessions online and they'll be recorded. So kama hakuna swali lingine, thank you very much. Yes, yes.
Someone is asking the time for tomorrow class.
Tomorrow's recap, 6 to 8. That's Gidi. Oh.
Yeah.
6. Let me just answer. Maybe.
Okay.
Oh, Meshika, 6 p.m. to 8.
Yeah. It's good to know so that I can plan around.
Oh yes. Oh yes.
Yeah.
Okay.
Thanks. Okay. So same time, even Friday, 6 to 8, 6 to 8.
Yes. Tomorrow
Okay.
and Friday, the recap ends.
And Saturday?
Saturday is normal class, so we'll have beginner probably in the morning. But now, depending on, since it's digital, I think we can play around with the time.
Okay.
Yeah.
Ayub, can I ask, for Saturday we do like 6 to 8 when you're sure everybody's in the house? Like,
for Saturday?
Everybody, yeah.
Or during curfew?
Yeah,
okay. Oh, during curfew.
The best time,
okay.
you never know where somebody.
Okay. So, Vinny, what I would propose.
Not that late, Buana. Some of us have families. We cannot keep office in the family. My boys are wondering what is wrong with me. They cannot even watch TV.
Yeah, I understand. Vinny, what you can do, trigger that conversation in the main WhatsApp group. And anyone who's joined this meeting and is not in the main WhatsApp group, please let me know. So that we can have a discussion and agree on the timings. So we need to trigger your conversation.
But the beauty is your recording. So I mean,
yes.
Worst case scenario, you are an outlier, or even if I'm an outlier, then I can pick up the recording.
Yes.
Okay.
Okay, guys. Enjoy your evening. See you guys again tomorrow.
Thank you.
Thanks as well. Bye, guys.
Bye.
Thanks.
Bye.
Bye, guys.
Okay.
Bye. Talk to you guys soon.
Yeah.